The next part of our gas law conversation, gas properties, has to do with the ideal gas law and how we're going to relate different variables for gases using this a relationship we'll call by that name. And what we're looking for is a mathematical relationship between pressure, volume, N and T, number of moles, and temperature for an ideal gas. This would again be part of our objectives for this chapter. We'll be looking at the ideal gas law to calculate pressure, volume, or moles of gas or temperature given the other three variables. We'll use that later to do the subsequent things, but not in this particular discussion. So we'll be looking for ways to relate those four variables for an ideal gas, noting that there's lots of different kinds of gases we might compare. Boyle's law, Charles' law, Avogadro's law. They gave us relationships between pressure and volume for Boyle's law, volume and temperature with Charles' law, and Avogadro's law. In each case, certain things, the other variables need to be kept constant for those relationships to be valid. So one way of thinking about that is that in the first one, the volume is proportional to the inverse of the pressure if moles and temperature are constant. The second law tells us that volume is proportional to temperature if moles and pressure are constant. The third law tells us that the volume is proportional to the number of moles if the pressure and the temperature are kept constant. And so what can you say? If N and T are the number of moles and temperature, the relationship with volume is shown here, proportional to NT divided by P. And that means that the volume is going to be proportional to, it's going to be a constant times N and T divided by P, and that constant is going to be given of the letter R. So it's directly proportional to temperature, so it's on the top, directly proportional to the number of moles, which is also on the top, and inversely proportional to pressure. Those combine together to tell us that there's going to be a constant times those things in that ratio, and that constant is going to be described as R. We call it the gas constant. And so if we rearrange this equation, perhaps you've seen this somewhere, this is our ideal gas law. It's quite simple to use, not very tricky algebra, thankfully. Pressure times volume equals the number of moles times R times T. Where does that take us? So we'll think back to where it relates to these other laws. So pressure times volume was going to be a constant, and so that means it's the rest of that relationship. Pressure times volume is going to be a constant. Well, N and T are a constant in Boyle's law, and so N and T times R, well, those are all constants, and so that's a constant. Or volume divided by temperature, the ratio of volume to temperature was going to be a constant. Well, if you have the number of moles and pressure constant, if you rearrange that equation, N and R and P are all part of the constant related to V divided by T, volume over temperature, or volume divided by moles when temperature and pressure are constant. So temperature and pressure and moles in this case all combine to give you a constant. So those are relationships that make some kind of sense, but you can incorporate R into what we describe, how they are described. Sometimes you'll use them this way, but we'll see where the more common ways are. The ideal gas law then is pressure times volume equals nRT, where N is moles and T is temperature. The R is the gas constant. And because it's a constant, that means it should be the same for all gases. R has a numerical value, and you're commonly going to not use quite all those digits, but there's a lot of digits for R. 0.0821 is probably sufficient if you wanted 3 sig figs, but the units are kind of exciting. You have to pay attention to them and make sure that you're doing things correctly. That means you need to use pressure in atmospheres, volume in liters, the temperature in Kelvin, and yes, moles, the number of moles. So those are all the other parts that are related to this gas law. If you put in ordinary conditions that we call standard temperature and pressure, standard temperature and pressure are defined as follows. The temperature is going to be 0 Celsius, which is weather in April in North Dakota this year, and that's 273.15 Kelvin, and ordinary pressure, which is 1 atmosphere. And so those two things are defined as standard temperature and pressure. It gives us a convenient way of relating different sets of conditions for different gases. So the conditions of 0 Celsius and 1 atmosphere are described as standard temperature and pressure, or STP, and experimental data will show us that at STP, 1 mole of an ideal gas gives a volume of 22.4 liters. It's bigger than a basketball, huh? And so it's a volume that's occupied by an ideal gas when you have 1 mole. We can call that the molar gas volume. If you wanted to take it a different direction, we could use this to determine R. If you rearrange the equation, PV equals nRT, or R will be PV divided by N and T, plugging in the values for the standard temperature and pressure. So there's standard pressure right there, the volume for 1 mole, and N would be 1 mole, surprise, surprise, and standard temperature is that, and you can calculate it out and come up with a value for R. Well, that's pretty close. 0.0821 is enough digits for most cases, but notice the units. You've got to be careful so that you're using the right ones, or your calculations will have problems. Be very cautious. So we were thinking about this from the start of this section. What is the volume of 1 mole of gas at standard temperature and pressure? The volume for the mole of 1 gas, well, there's a bunch of gases shown here. Hydrogen, helium, ammonia, nitrogen, fluorine, argon, carbon dioxide, and chlorine. Well, they're close. I wouldn't say they're all exactly 22.4 something liters, but they're right in there. And so it relates to 1 mole again, and the standard pressure is 1 atmosphere, and the standard temperature. At standard temperature and pressure, we're expecting the volume to be this much for 1 mole, 22.4 liters, assuming the gas is ideal. And so there are times when gases are more ideal than others. We will not be looking for perturbations to that right away. That will be a very small subset of our discussion for this topic. So most of those are going to be quite close to 22.4, but some differ a little bit more than others for reasons that we'll leave for another conversation. All right, so given this kind of information, can we use this to determine the number of moles of methane gas in a storage tank with a volume of, wow, 1.000 times 10 to the 5th liters at standard temperature and pressure? Or how many grams will that be? Well, that'll take us a minute, but let's see if we can work it out. So how we set up this problem is using the ideal gas law. We're looking for N, the number of moles, right? Which is, in this case, going to be methane gas, and it's pressure times volume divided by R times T. So the pressure is shown to be 1 atmosphere if it's STP, standard temperature and pressure. The volume is given here as 1.000 times 10 to the 5th liters. It's a big number, but oh well, it's a storage tank. The value of R is a known value, and I'm going to put in 3 sig figs worth, liters times atmospheres divided by moles times Kelvin. And then standard temperature would be 273 Kelvin. If you've done this carefully, the units will make sense. We're looking for moles, right? And our atmospheres will cancel, and liters will cancel. Kelvin cancels because those are both the denominator, and all that you're left with is the unit of interest, which is moles. And now you get your calculator out and give it a shot, see if you can do it. Okay, to complete the question, then you've had to punch it into a calculator to determine that you'll get an answer of a very large number of moles. All right, but they've asked us to determine more than the number of moles. They want to know how many grams. So you need to know molar mass. 1 carbon and 4 hydrogens should be 16 grams per mole. If you multiply these two numbers together, you'll cancel out the moles, and you get an answer in grams. Again, pay attention to units. It will make a big difference in your success in these kinds of calculations. All right, let's try another one. Let's say we have a sample of chlorine gas. It's a volume of 946 milliliters. It has a pressure of 726 millimeters of mercury. Don't you just love these interesting numbers? And we want to determine the pressure of the gas in millimeters of mercury if the volume is reduced at a constant temperature down to 154 milliliters. So what you want to do in these kinds of problems is to set them up carefully. So pressure 1 is 726 millimeters of mercury. Be sure the units are always the same. Volume 1 is 946 milliliters. Write them out in a chart or label them in your problem in some fashion so you don't lose them. Let's see, that was millimeters of mercury for the pressure. The second set of conditions, pressure 2 and volume 2, we're looking for pressure 2, so that's the one we don't know. Volume 2 is 154 milliliters. Now notice for gas laws we will commonly use liters, but if your volumes are both milliliters, then it won't be a problem because the way we set these up, they will cancel out. And so pressure 2 is the one we're looking for. Remember the relationship between pressure and volume. Pressure and volume multiplied together are going to be a constant, so pressure 1 times volume 1 is the same as, going to be equal to pressure 2 times volume 2. Ready, set, go! All right, next one. So we're going to look at pressure times volume as a constant. Pressure 1 times volume 1 gives pressure 2 times volume 2. But given the numbers as we stated it in a neat fashion here, pressure 1 and volume 1 are shown. Pressure 2 is unknown. Volume 2 is given in the equation. And so now you'll take that relationship and rearrange it to give you pressure 2 equals pressure 1 times volume 1 divided by volume 2. Put in the numbers. If this all works as it should, notice the things that are going to cancel. The milliliters will cancel when both units of volume are the same, and your answer will be in millimeters of mercury, and that's all you have to do on that. Okay, this is actually not completely an ideal gas law problem because we didn't need R here, and there was 2 sets of conditions, but it's related to the gas law. I hope this is helpful to you as you begin your assignment and working on things with gas laws. Paying attention to units will be very important, essential. Good luck on your assignment. I will hope to hear more questions as they come up, and I'll see you in class.